All right, hello everybody. How are you doing today? I just wanted to say really good job on the last chapter. We did an entire chapter online, virtually, and you guys did a great job. You really did. I got two more to go. I want to get through exponential functions and rational functions and get you all ready to go for pre-calc next year. So, I'm going to today talk about exponential functions. And exponential functions and equations are very interesting because they're very relevant, actually all the time, but especially now. There's one big exponential function that we're dealing with, and that's the coronavirus. And it kind of explains what an exponential function is. They say it grows exponentially when it doubles or triples. The more people that have it, the more people that can get infected. Now, we want that growth rate to be as small as possible, and eventually we want it to become less than 1, like a half. It means every time and every day to go down by half and half and half. That's the leveling off number. And I'm going to show you what all that kind of talks about. So we're talking about growth and decay, essentially growing and decaying, coming down. Our general form from an exponential function is this. The a value is a starting value. So if you think about the virus right now, it had to start somewhere, and it had to be a certain amount of it, a certain amount of people infected, and then more people got affected because of the b value. The b value is the growth vector. So if b is greater than 1, it's growing. What we want to happen is we want it to start decaying or being less than 1. But it has to be greater than 0. I'm going to show you why that's true. All right, now I want to show you what an exponential graph looks like and how we can change it. Notice here in orange, I have this line. It's not much going on there. It's just flat. A and B are both 0. And here's our standard form of an exponential equation. Well, 0 times 0 is going to be 0. That's why nothing is happening. If I change the A, guess what? Nothing is happening. Why? Because B is 0. And 0 times anything is 0. If I change B, that looks like a little bit changes. Like now it's going off in both directions. And then when I get below 0, it all disappears. We'll explain that. We'll talk about that in a little bit. But right now, let me say, I'm going to put B back at 0. Now I'm going to set B equal to 1. Let's get there. Okay, and I'm going to change A and watch what happens. It just goes up and down. Notice when A is 5, it crosses right through 5, right there. Boom. When A goes up to 10, it crosses through 10. So A is the y-intercept. Now don't get confused. It's not always the y-intercept, not like a linear function. But it's a starting value. We kind of call it a starting value. And I'll explain what starting values mean in a little bit. Let's say we start with 2. Now watch what happens when I change the b. See how that 0.02 stays there, but look at the rest of the graph. It's just going up. The b is the scale factor. Every time b increases, it goes up faster. So if I left b equal to 2, the idea would be that every time I go over 1 on the x, I double or multiply by 2 the value of the y. So we started at 0, 2. So if I go over to 1, I should double it and get 4. If I move over 1 more and I double 4, I should get 8. And so on. It continues to double. Now you can make it 3. It means you triple it. It started at 2. If I triple 2, or multiply it by 3, I get 6. So watch, I went over 1, and now I'm up to 6. Then I multiply it again by 3, 18. Can't even see 18 on the graph. Okay? So exponential functions shoot up super fast. Or, watch what happens. So when b is 1, it flattens out. So when b is 1, it flattens out because it's not changing anything. B is staying the same. A is just staying the same value because b is not changing it. When I move it less than 1, oh look, it goes the other way. Now notice the 0.02. The 0.02 is not changing. This is just either going infinitely larger, it's going down. But look how it's going down. Is it going down forever? Or does it level off? Think about it. Let me try to make b into 0.5. That's a half. That means I'm starting at 2. When I move over 1, I should multiply it by half, or which is the same as dividing by 2. So half of 2 is 1. If I move over 1 more, I should get half of 1, which is 1 half. Every time I move over, I'm taking half. 1/4, 1/8, 1/16. So in theory, do I ever get to 0? If I just keep taking half of something forever and ever and ever, I'll get 1/16, 1/32, 1/64, 1/128, 1/256. Eventually I'm going to get 1 over an extremely large number. But is that equal to 0? In theory, it never equals 0. It flattens out. And we have a name for this line where it flattens out. We call it an asymptote. So it flattens out at 0. It never reaches 0, but it gets closer and closer and closer and closer to 0, but never quite gets there. Now look what happens when b is negative. Oh, when it's 0, it's just that line that starts at 0, and then it disappears completely. Why would b disappear, or why would the graph disappear when b is negative? Okay, I want you to think about that one. Maybe I won't tell you that one. Just think about that one. We'll get to that one later. But what I want you to know, when b is between 1 and 0, the graph is what we call a decay. It's going down because we're taking a fraction of it, like a half or a third. It's just going down. When b is greater than 0, it's going up. So can you think of a couple things right now where exponential increase is happening? Oh, I don't know, maybe population of the world. At the end of this video, I'm going to tack on it's about a 3-minute video on the world population trend. It's very cool. I'm putting it at the end. If you watch it, great. If you don't want to watch it, don't even bother. Just stop the video and don't bother watching it, but it is kind of cool. The virus. Why are we all sitting at home and not in class? Because the virus has an exponential growth rate of contagion. And what we're trying to do with social distancing is stop that growth factor from increasing and try to level it off. And hopefully, maybe make it go down. But we're only talking about one type of exponential. It's either going to grow or it's going to decay. All right, now that you've seen that, let's do our own. 2 to the x. Remember, your b factor is 2. That means it's going to be growing by a factor of 2, which really is basically pretty straightforward. What it means is it's just going to keep growing by 2. Now let's make a table, because I like making tables. Tables show you kind of how a graph works. So let's say x equals 0. Well, what's 2 to the 0 power? Well, anything to the 0 power is 1. So what's 2 to the first? It's 2. Now notice, this is increasing by a factor of 2. We are going up by 2 every time. 2 squared is 4. So the next number would be 8. Just going to keep going up by 2. All right, let's take a look at that graph then. 0, 1. 1, 2. We go over 1 in doubles. 1, 2, 3, 4. And then 4, 5, 6, 7, 8. So that, even though I missed the point, sorry, is our growth factor. Now, we saw in the video, this thing levels off at 0. Okay? It doesn't actually hit 0, but that's what it's getting close to. So our domain is everything. There's not an x value that's out of play. But for the range has to be greater than 0. And for your standard function of exponential function, your standard equation of exponential functions, this is always true. Let's look at another one. Now that b is 1/2. That's what we're hoping to get soon, because that means every day there's half and half and half. It's a decay problem. Now there's no number out here, just the same way there was no number in the previous problem, so we assume we're starting with 1. And it kind of makes sense. What's 1/2 to the first power? I'm sorry, to the 0th power is 1. So what's 1/2 to the first power? Well, that's a half. Some of you guys like to think of it as 0.5, which is fine. But what's happening between these numbers? Each time they're being divided by 2. 1/2 to the second power is 1/4. And so on. Every time we do it, we're going to divide it by 2. So it's going to keep going down and down and down. So when we graph this one, what's it going to look like? Okay, let's change the scale a bit to make it look a little better. Let's say, 1, 2, 3. Let's make this 1, 1, 2, 3, and this is 2. That's just easier to graph. Now we don't have to change our y scale, or I'm sorry, x scale. We're just going to change our y to make the graphs fit. So 0, 1. When x is 1, we have a half. When x is 2, we have half of that, which is 0.25. And so on. It's going to be always half and half and half. But if you keep taking something half forever, does it ever end up being 0? In theory, it does not. Our domain is everything. Our range is everything that's greater than 0. So unless you shift the graph down with another method, you can never have a value less than 0. And think about it in population and stuff. Can you ever have negative people? Okay. It doesn't mean every exponential graph is positive, and I'll show you examples where it's not. It's just the general ones that we use, that's what we assume. So now we've got 3 to the 2x. Alrighty. So we have 3 times 2 to the 0. Well, 2 to the 0 is 1. Because anything to the 0 is 1. 1 times 3 is 3. So our starting value is 3. Right? And our scale, or our growth factor, is 2, which really means it's going to be doubled every time. It's going to be 6. Then it's going to be 12. Then it's going to be 24. But remember, that all comes from the formula, or from the equation. 2 to the first. 3 times 2 is 6. 2 squared is 4. 4 times 3 is 12. If you have a growth factor that's easy to do, you can just double it or triple it or take half of it or whatever it is. Your growth factors aren't always that easy. Sometimes they're 0.75 or 0.36 or 1.7. So you do have to use a calculator and multiply these through. All right, this is a giant scale. This is going up fast. So let's do this. Let's make this scale all go up by 3s. So we have 0, 3, 1, 6, 2, 12, and nothing else fits on the graph. And what does it level off at? Of course, 0. Domain is everything. Range is greater than 0. Oops, that's a terrible one. I was priding myself in doing really well with them, and all of a sudden that clunker gets thrown in there. Okay. Notice we're starting with a value of 3, and our scale factor is 1/3, which means all right, 1/3 of 0 is 1. We're starting with 3, like you kind of figured. But our scale factor is 1/3. It means every time we go on, we're multiplying by 1/3, which means the same as dividing by 3. So if you think about it, we're dividing by 3 every time. So 1/3, it's about 0.667. Think about that. 1/3 squared is 1/9. 3 divided by 9 is 1/3. All right, we don't have to go any further. It's another small number. We put in 3. We're going to get 1/9, which is 0.111. All right, let's graph these. Is it a good scale, or should we? 1, 2, 3. That's probably a good enough scale. We'll just have to do it like that. Put in 0, you get 3. Put in 1, you get 1. Put in 2, you get 2/3. Put in 3, we got something really low. Remember, these are sketches. I don't expect them to be perfect. In fact, what I just drew was something relatively impossible. I actually hit 0, kind of, but we know in reality it's never supposed to hit 0. The domain is everything, and the range is greater than 0. Whoa, almost did it again. Not the greatest, but you can kind of tell what's going on right there. Okay. So notice we're adding more to this. So I'm going to stop that video for now. That was enough. See if you got the basics down. And when you come back to watch the next video, we'll be doing more stuff to these. So have a good one.